Well, this is lesson 7 for Unit 3 on derivatives, and in this lesson we're going to look at how to take derivatives of inverse functions. And we're actually going to start by just taking a one page just to get comfortable seeing how do inverse functions actually work again. So on the left I've got just some random everyday function, and this one is the square root of x plus 3 and then add 1. And we're going to be doing a little calculus on this, so we might as well prepare it, get it ready to go. We'll think of that root as being x plus 3 all to the 1/2, and then add 1 more. And we're going to graph this function up here on this graph. I've got my axis. I know this is the x-axis, but I'm going to call this the in-axis. It's what goes into the function, and here's what comes out of the function. I want to label it that way just to get in the right mindset for doing inverse functions. So for this particular function, this f of x, it's a square root that's been shifted a little bit. It's 3 back and 1 up. So it actually begins its journey right here. And then we go 1 over 1 up. And from the origin, it's actually 4 over and 2 up. And that would put you right there. And it's just your typical square root graph, which is going to go kind of like this. It's a parabola on its side, of course. Just like that. It keeps on going to the right. And we could talk about the domain and the range for this function, right? The domain would be what values for x are actually acceptable, what values can go into this function, and the answer is, well, you got to make sure your x's don't cause negatives under the root. So x's need to be greater than or equal to -3. Equal to -3 is fine. We can take the root of 0. And then the range. What numbers do we actually see coming out of this function? Well, the y values, if you wish. Looks like they go from 1 up, and we do actually see a 1 come out, so greater than or equal to 1. Now there's one point on here I just want to take a look at, just kind of watch what happens when we look at the inverse of it. Just f of 1, seeing what happens there. We would be putting 1 into the function, so we would be going square root of 1 plus 3, then add 1. Okay, root of 4 is a 2, then add 1, and we end up with this value of 3. And sure enough, that point is like right here, right? Okay, so just that one evaluation tells me that here's one out of many, here's one point that is actually on the graph. And again, I just kind of want to watch this point, right? I've got 1 going in and then 3 coming out. And let's literally label it that way. For this machine, the x's go in and out spits this 3. Okay, fantastic. We're going to be taking a look at the tangent line right at that one point at 1, 3. So I'm just going to go and draw that tangent line in right on my graph right here. Okay, so that's my tangent line. And if I wanted to find the equation of that line, I definitely would need to know its slope. Let's go and do that. Let's get ready to do some calculus here. We'll take a derivative, right? The derivative of this function called f. So f prime of x, if we take that derivative, it would be 1/2, and then there's that blob, x plus 3, all to the -1/2, and then the plus 1, well, you take a derivative of that, you get 0. Okay, well, let's just check out what the slope is doing for that tangent line. Just kind of curious to see what that slope value actually is. So f prime figured out at 1 for x, that'll be that point, 1, 3. I would have 1/2, 1 plus 3 all to the -1/2. All right, that's going to be 1/2 times 4 to the -1/2. So I have to root the 4 and I have to flip it upside down. So that'll end up being 1/2 times another 1/2. Hey, we're going to get a quarter. So it looks like the derivative of this function, at least at that one point, is actually going to be 1/4. And looking at that red tangent line I've drawn in there, yep, that looks about right. It's got a slope of a quarter. You go 1 over, it goes a quarter up. 1 over, it goes a quarter up. Or another way to say it, you'd have to go 4 over before you finally go 1 up. And I'm going to label this that way. And so, yeah, you can think of this as a rise over a run. You rise by 1 unit when you run by 4, at least at that one point. Okay. Now, let's take a look at the inverse function. To come up with the inverse function, you would need to flip that graph around the line y equals x. You need to interchange x and y in order to find out what that inverse function is. So the inverse function, it turns out if you flip the algebra around, ends up doing this. Inverse function denoted that way ends up being x minus 1, remove the 1 that was added on last with the function, square things to get rid of the square root, and then take away 3. That's exactly what you'd find if you interchanged x and y and then solved for y. Now, let's just watch what happens with the domain and the range for this new thing, this inverse function. It's a totally different function, right? In fact, let's graph it. Right? If we go ahead and graph it, this is going to be a parabola, but I'm only going to graph one side of the parabola. The vertex is actually right here, 1 over 3 down, and then we're going to go 1 over 1 up, or from the origin 2 over and 4 up, which would put us right there. Okay, and so this inverse function is going to look like this. And this graph also has an in-axis, numbers go in, and then numbers come out. And the whole idea is that this function should undo what the first function does. Now, when you go to find the domain and the range for this inverse function, I guess you could go and look off the graph and say, okay, yeah, what do we see for the domain and the range? But there's even a better way. Everything about these two functions interchanges with x and y. So the domain becomes the range, and the range becomes the domain, right? That's how this game works when you go for inverse functions. So if the range used to be y is greater than or equal to 1, that's going to be the domain on this one, greater than or equal to 1. And if the old domain was x is greater than or equal to -3, now y is going to be greater than or equal to -3. And we just see all of those things just interchanging with each other. All right. Well, let's see if we can go and check out that one point again. I'm just kind of curious to look at that point. It's not going to be 1, 3 anymore because this machine is supposed to reverse what that function f does. So if I want to talk about that same point, the point that used to be right here, okay, that point now is going to be sitting over in this spot right there. You see, now I would say, okay, well, what happens if I put 3 in to this inverse function? Well, following the rules here, I would go 3 minus 1 squared, take away 3. So 2 squared is a 4, take away a 3 is going to be a 1. My point with this is everything is reversing, okay? Just the ins and the outs, the x's and the y's, the range and domain, everything is getting reversed here. Now, the point that used to be 1, 3 is now 3, 1. And you can think of 3 as being the number that goes into this machine, and then 1 is the number that comes out. Okay, the derivative. Let's try to find the derivative of this inverse function. It gets a little messy. It's not impossible, but it gets a little messy doing Isaac Newton's notation on this, and Leibniz might be better. It might be safer to say, hey, let's use the notation where we say, let's do a derivative of the inverse function. You know, for the Newtonian way of writing it, it's kind of like, oh yeah, okay, I've got the inverse function, and then I need to do a derivative of that. Just kind of a weird deal with the apostrophe on top of that f to the -1. Well, you can do it. All right, taking a derivative. Well, looks like the chain rule here, the 2 is going to come down. We'll have x minus 1 to the 1 multiplied by a 1. It's basically just that. Okay, now let's go and check out the slope at that same point that we've been kind of watching bounce around. I'm going to use Leibniz's notation. I think it's just a little easier to work with. So I'm going to go and do the derivative of the inverse function evaluated at that place. Now, over on the left side of your page, that was when x was 1, but here it's when the input number is 3. Okay, you know, I think we can just drop these numbers in here. It's going to go pretty quick. 2 times 3 minus 1. Okay, 2 times a 2, and we end up getting a 4. So let's just stare at this thing here for a second and see what this is saying. Right? That 4 is basically saying 4 over 1. And so the tangent line here is very steep, right? It has this slope of 4. Just going to sketch that in. That's going to end up looking somewhere like this. And so the old graph used to go 4 over 1 up, right? Just kind of looking at it, right? Like go for a walk of 4, and then you go for a rise of 1. This one is the other way around. You go just for a walk of 1 for your run, and then you go up by 4. Everything seems to be completely flipping around, x's and y's, including this rise over run. So we see a rise of 4 when we see this run of just 1. This really is the exact same point, right, that we're playing around with. So we've got on this side of the page, let's grab a highlighter here. On this side of the page, we're talking about putting 1 in, and then over here, we're talking about putting 3 in. But it really is the same point, even though it looks like we're putting different numbers in. And that's going to be important when we get to the next page. So it's the same point, right? Exactly the same place. But when we look at these functions, it's different in numbers, if I can call them that. On the function, I have to put the 1 in. On the other one, I have to put the 3 in. Well, what it's going to come down to is, if I want to find the derivative of that inverse function at 3, if I want to know that the slope is 4, right, if this was my goal to find that, I could have instead found this number and just flipped it around upside down, right? And said, oh, maybe it's easier to find the 1/4. And I can just flip it and say, oh yeah, the answer is 4. But you just have to be careful about, oh, well, are you talking about at 1 or at 3? And it depends which function that you're actually working with, whether you're talking about the original function f or whether you're talking about the inverse function. So that was kind of a specific example first. Now let's kind of look at the generalities here. I've got just a little graph, and it's going to have a function and its inverse. And this dotted line here is the y equals x line that graphs get mirrored around when you're trying to find inverses. And I'm going to say that this could be my f of x graph right there, which means this one, once it's mirrored around, is my inverse function that will undo what the first one does. Now, just some values. Let's say that this is a and this is b. And if I go and actually put these numbers, into the functions, like right here, this blue dot, that's what happens when a goes into f. And up here, this would be f of a. Okay, that's great. Now, I can see, though, that that's going to get mirrored over to here. And if the x value there is b, then I guess the y value for this one would also be b. And then looking at this another way, right, okay, here's a going in, right, and we have that value come out. If I wanted to see that same spot, that same a, that's actually going to show up here. And that is going to be what happens when you do the inverse function of b. So just different numbers going in and going out, right? Inverse function, looking at this graph of b, yeah, that's inverse function of b, but it's also equal to a, because that's how tall that is. Okay, here's the approach. It is way harder to write this down or to talk about it than it is to actually do it. My way of remembering this, that a lot of students like, is I like to call this process flip, flip, flip. We're going to do 3 flips in order to find what the answer is. It's going to be tempting to only do 2, and you have to make sure that you flip 3 things around in order to come up with the right answer. So if we're going to try to find the slope off this inverse function, right? That's kind of the goal of the day, is could you come up to this graph and find the slope of that inverse function right here? The answer is sure. Why don't you instead look at the slope of the other function, the main function, but then we'll just reciprocate our rise over run, and then we'll have the right answer. But we'll have to be careful about which point's going in and which point's coming out. Here's the way that I would write this down. First, we'll do it in English. and then we're going to write down the calculus. And I don't know if one is better than the other. Maybe just the on-the-job training down in example 1 is the best. But here's what's true. The derivative of there's a lot of writing here, so keep it fairly small. The derivative of an inverse function, I'm going to abbreviate there, save some space. That's our goal, right? How do you find the derivative of an inverse function? Well, it's equal to the derivative of the other function. So here's my first flip. The other way, and by that I mean reciprocal, at the other point. And it's that last other that a lot of people miss. Okay, geez, that's a lot of words. I don't know if this is going to get any better when we go to write this down, but here's what it would be like if you go to write this down. So the derivative of an inverse function, if you have to work on that, dx. Now we're going to play with this one little blue dot that you see up here, right? That's at b. Okay, so figured out at x is equal to b. So b is a number that's going to go into the inverse function. If I was Newton trying to write this down, oh, it gets a bit messy. But you could say, okay, I've got my inverse function, and I need to do a derivative to it, and then I want to figure it out at b, please. Okay, here comes the triple flip. We are going to flip upside down, so I need a fraction here and put 1 on the top, and we're going to go underneath that 1. We're going to reciprocate. That's my first other. And then we're going to go and work with the other function, just f, right? We'll work with its derivative, not f inverse. And then we're going to figure it out not at b, but at the other point, right? So a whole bunch of little flips here. Let's just put them all into place. So this middle other, where it says, hey, we're going to do a reciprocal. Yeah, so that's why it says 1 over. And when it says, oh yeah, we're going to do it at the other point. So this other right there says, oh yeah, don't do this at b, do this at a. And the other function says, well, you don't have to work with the inverse function of f. You can just work with f if you think that'll be easier to work with. Now, one last thing that may throw you off, right? And it's this issue of make sure you go with a and not b. There's another way that you can write a. And so you'll sometimes see this in textbooks. And if you haven't been confused so far, geez, this will probably complete the confusion. We could do a derivative of f, put that down in the bottom of a fraction. And then when we're trying to figure out, like, well, what would the a be? How could I actually find out how big a actually is? Well, a is actually the inverse function's value, not a derivative, just its value at b. So we could go and install in here f inverse of b, which could be handy because you're supposed to do this at b. So if they say do this at b, well, then that could go, in here, right? And then you'd be ready to go. So there's a triple flip that's going on. I know it really does look confusing, but it does turn out, and we'll see this in just a second, that these two things are the same thing. Either this inverse of b or just a, right? Those are identical. Okay, here we go. Example 1. Let f be a differentiable function with values in the table. If the function g is differentiable, and okay, so g and f are inverses, right? They're actually inverses of each other. If g is the inverse of f, then f is the inverse of g. They interchange that inverseness. And they're asking you for the derivative of g at 3. Now, I'm noticing that, there's no column here, right, where it says, oh yeah, let me tell you about the derivative of g, right? It doesn't have that in the table. So we have to find some way to work with just f, its partner function, in order to find out what that derivative will be for g. So here goes. The request is that you go and find g prime of 3. Another way that you could write that is, what is the inverse function's derivative at 3, right? Same thing. Okay, well, we're going to play the flip, flip, flip game. So first of all, we are going to flip this upside down. So I'm going to go 1 divided by. I'm going to flip to the other function. I don't want to work with g. I'd rather work with the derivative of f. After all, that's in the table. Now, the last thing, don't put a 3 here. This is the common mistake. People go, oh, we're doing this at 3, right? Now, 3 was the number that goes into g. It's not the number that we want to think about going into f. There's going to be a little interchanging that's going on there. So just a little warning, okay, as we go to do this. This is probably the most common mistake right there. So I'm going to put a little thought here. Looking at this, 3 goes into g. So ins and outs reverse with inverse functions. So if 3 goes into g, then 3 comes out of f. So I'm going to go and try to find just the right row in the table, and I want to tell you which row you do not want. Don't grab this row. And you're like, yeah, but it says x is equal to 3. Yeah, those are numbers that can go into f. We want numbers coming out of f. So we actually need to spot this place right there. That is what tells me we're on the right row. 3 is actually coming out as a y value for f. So it's this row that we want. I'm actually going to be putting 6 into this, right? That's the number that I want to look at. And so the answer, geez, this is super easy to do. This is just going to be a 1 all divided by, okay, derivative of f at 6, done, a -2. Okay, we're done. The answer is -1/2. But you have to make sure you do a triple flip there. We're flipping upside down, we're flipping to the other function, and we're flipping to a different point, right? So I don't want to get suckered into using the 3 for that one. Okay. Inverse trig functions. This is going to be a page of some information that you just simply have to memorize. There's no nice way around this. We do need to know what the derivatives of inverse sine, inverse cos, and inverse tan are. And you can use the technique I just showed you to find it. You can use implicit differentiation to get there. That works too. But we just eventually need to know what the answer is. So first of all, let's just talk about what this function inverse sine is actually accomplishing. Looking at sine, here's a small section of the sine graph. Generally with sine, you put angles into the machine. Now, if we were in Math 11, we'd be thinking about degrees. You put 30 degrees in, and then you do sine of that, and it says, oh, 0.5. Okay, and so then this thing kicks decimals out. It says, oh, okay, here's your answer. So if you look at the graph, we've actually got the output axis being decimal values from -1 to 1, and the input axis is actually angles. Inverse sine reverses that process. The whole idea is you could put in a decimal in. You could say, hey, I'm trying to find the angle here, but I know sine of it is 0.5. And you say, what's the inverse sine of 0.5? And then this machine runs and it goes and kicks an angle out. It would say, oh yeah, the angle's 30 degrees, or pi over 6, right? We should be thinking about this in radians. But decimals go in and then angles come out. So the axes here are reversed compared to the other one. That's how inverse functions go, right? Decimals in. That's what that machine does. If you were to reflect this graph around that y equals x line, that'll be enough to tell you what the picture is going to look like. And the picture ends up looking like this. And it does terminate, it stops. It doesn't keep on going. Just does that much of the graph. So that's what's going on with inverse sine. And you need to know its derivative, plus the derivative of inverse cos and the derivative of inverse tan. This is not the same thing as cosecant, secant, and cotangent. Those are reciprocals, right? Now we're talking about not functions that are upside down, but functions that are, well, inside out. Okay, the derivative of inverse sine to be memorized is this: 1 on top of the square root of 1 minus x squared. I didn't say it was going to be short and easy, but that's what that one is. Just so you know, there is another name for inverse sine. Okay, this thing right here is also called arc sine. So sometimes you'll see people call it that. That's arc sine of x, that inverse sine. And names for these other ones here: cosine, inverse cosine is often called arc cos. And you guessed it, arctan. Those are some pretty common names actually in the math world for those inverse functions. Okay, the derivatives that you need to memorize, you got two more. The derivative for inverse cos is actually -1 all on top of square root of 1 minus x squared. And the last one, the derivative for inverse tan is, there's no roots in this one, it's 1 all over 1 plus x squared. They simply have to be memorized. There's no way around it. Just have to memorize those ones. Okay, let's see if we can use that idea to find some derivatives here, and then we'll finish up with this page. So instead of just saying, all right, have you memorized it? Here's a question about, inverse sine. We maybe will throw some chain rule stuff in there too. And that's certainly what's happening with this one. When I look at it, I can see that there's this blob here going into that machine. Actually, all of these seem to have some nice blobs, chunks of algebra, interior functions going in. This one too. Okay, so we get to do chain rule for every single one of these. First one, doing the derivative of inverse sine. Well, start to memorize it. I know it's that 1 over the root thing, right? That's what happens if it's just an x. Well, it's not just an x. It's a 4x plus 3. So that's okay. Just fake it. Just say, it's probably going to roughly follow that pattern. So I'm going to go like this. I'm going to put my root there. Get that all ready to go. Now, I'm going to just follow that pattern, and I'm going to go 1 minus 4x plus 3 squared. So I've just literally followed the pattern using the blob, but that was cheating. I just wrote something down treating that blue blob as if it was x, and it's not. So now I need to go and multiply by the derivative of that blue blob. I have to make sure everything I just wrote down here gets kicked with a 4. And that would be my answer for that one. The one beside it, same plan. I know generally it's 1 divided by, and then the root. Okay, it's 1 minus what you put in squared. So 1 minus, and then what am I putting in? Oh, a big mess. 1 minus, looks like the root 3 is not on top of, the root's not on top of the x there, just like that. And that would get squared. Okay, great. So there's that blob, just sitting there, following the pattern. That's cheating though. I just wrote that down pretending that that blue blob was x, and it's clearly not. So now I have to multiply by the derivative of that blue blob. Well, the derivative of 1 is 0. It's wasting our time. And then this is really just a linear term with an irrational, awkward coefficient. So we're just going to have, multiplied by that derivative, which would be minus root 3. 2 more, and this thing's done. Okay, a cosine one, same pattern, but it's going to have a -1 on the top. So we'll have -1 sitting on top of, oh, that was a little messy there, try that again. Square root. Okay, this is going to be 1 minus that thing, that blob, 4 root x squared. You could have just simplified that, right? 4 squares to a 16, the root x squares to just an x. I could have written 16x there. That would be fine. Either way, this works too. But I just treated that blue blob like it was x. So now right away, I have to go and multiply by the derivative of that blue blob and put it right here. The 4 is going to hang around. Then the derivative of the x squared, that would be 1/2 x to the negative 1/2. There, it's a mess, but that is the right derivative. At least I don't have to do any limits. And then the tangent one. Well, the tangent one doesn't have any roots. It just says 1 divided by, and then it's 1 plus the item squared. So 1 plus, if it had just been an x there, I could have just gone x squared, but here's this weird blob. Root of 5x minus 3, that's going to get squared. So yeah, you know, did I have to write that? No, I could have removed the square root when I squared. They're just going to undo each other. But I just wanted to do that so you could see the blob, right? Just following that pattern, doing nothing but following the pattern that you can see, you know, up here, right? 1 over 1 plus what you put into the arc tangent squared. But that was cheating, so I now need to fix this. I have to multiply by the derivative of that blue blob. Oh, that's a chain rule. So I'm going to have times the 1/2 comes down, and then 5x minus 3 to the negative 1/2. And that was cheating again. I just treated that 5x plus 3 as if it was an x, and it's not. So then I would pick up another 5. Didn't say it would look nice. I just said we would be able to do it. And that takes us to the end of this shorter lesson today, just looking at inverse functions. So a couple of thoughts. If you're doing derivatives of inverse trig, you just have to know these three. Okay? They simply must be memorized and ready to go at any time. If you're doing a derivative of inverse function and you really don't want to work with that inverse function because maybe you don't have access to information or it's just awkward to work with, you could do the derivative of its partner instead. Just reciprocate your answer, but you gotta go at the opposite point. You have to think about the ins and the outs. And that finishes up our lesson.